Okay, guys, welcome to today's class. Today we have nothing in preparation because I was a little late. This is an analog voltmeter. আজকে video একটু কাঁপবে, but please forgive us. So this is a rheostat, all right? We know it's a rheostat because it has it written here, rheostat. So rheostats are also written as variable resistors. That's আমাদের mystery student হাত ব্যথা যাচ্ছে. Let's just give this a minute. Let me just fine tune this so that I have more field of view, so you guys can see more than just what we usually see, because we'll need extra space for this one. Okay, yes, this works. So this is a rheostat. I'm going to quickly explain this. So there's a fixed resistance between these two connectors. Why? Because the wire is looped from this end to the other end constantly. And this is basically the sliding contact that we move along a rheostat to measure the resistance. Now what happens is there's basically three contacts here, 1, 2, and 3. So if I connect something between these two, then the resistance between these two will not change, right? So here we have the voltmeter that we're going to use to do our calculations. And alongside that, we have a battery, right? A 9-volt battery. So I'll be connecting this to the negative terminal of my battery. And then basically, okay, let's first set up this circuit. So what I'm going to do now, I'm just making this stuff up as I'm going along, so like, I'm not exactly sure. Okay, so let's make life easier, specifically for me, by first drawing a circuit, right? Then we'll move on from there. Okay. So first of all, this is our rheostat, right? Variable resistor. So we can show this as a sliding contact, and this can be A and B, right? So when I draw this A, B, and C, what I basically mean is this is A, this is B, and this is C. So firstly, let's make a really simple circuit. যেটার মধ্যে I will provide, say, a circuit voltage, power supply between these two, like this, and I'll measure the voltage across these two. So, mystery student, what do you think will happen? So if this is my voltmeter and this is my battery, so what I'm going to do is I'm going to connect it across these two. So I'll wrap this, okay, I'll just click this here. I'll put this here. This. Today is a total mess. So, mystery student, is it working? Yes, it works. I'll just reverse my battery. Okay, so now let me explain what I've done. What I've done is basically I've had a voltmeter. The voltmeter is connected across, if you notice this, these two terminals of the rheostat. And this is basically similar to the voltmeter connected across A and C. And then I'm connecting the battery across these two terminals also, right? Yeah, I'm good. So now, when I connect this, what happens is, if you notice the voltmeter, it's almost zero. It's not exactly zero. This is basically a zero error, right? It's a positive zero error. So what's going to happen here is, I'll just keep that circuit outside so that you can actually see the circuit. Yeah, okay. All right. So as I increase the resistance, basically if I move this along here, the resistance between this and this contact will increase. And as this increases, this value should increase, all right? So here I am with my battery. Here's the battery. And I connect it here, and voila, you see, start getting a reading. So as I move this further, it's varying because the connections between the two ends isn't really good, but it roughly gives you the idea. All right, we're going to do this again. We're going to start from 0. So when this is at 0, the reading is almost 0. So as I slowly increase this, I'm going to keep sliding this. You're going to see this reading moving up. And why does the reading increase? That's because the value of the resistance between these two terminals is increasing. So see, it was around 0. Now it's around 2.5. Very bipolar. And yes, moving on. If I increase this, this goes on to around 5 now. And then if I increase this further, this keeps going up. right? So the highest this can go, I think you guys can see it, is if I go completely to this end. So when I go completely to this end, basically we have maximum resistance across these two, and specifically it's 100 ohms as written here. So this leads to a voltage of 9 volts across the two terminals. And again, if I decrease this slowly, this value will decrease down to 0, right? I'm moving this along and this decreases. So what I actually wanted to show with this was another voltmeter to show how the voltage across this varies. Okay, give me a minute and let me try to set that up too. Right guys, I need your patience because, oh look, it's another voltmeter. So this is going to take a minute of my time and a minute of your time too. So basically what I'm doing now is I'm adding another voltmeter across these two ends of the rheostat, right? So basically this is one wire and okay. Oh, nice. Right now, guys, if you notice this, there's basically 2 voltmeters now. Oh man, duita eksathai dekhani jacche na. So, okay, so let me explain what's going on now. Basically, we have 2 voltmeters. One is connected across this and this. So it's basically measuring the resistance across this much wire. And another voltmeter is connected across this and this. So what's going to happen is, as I move this, one of the voltmeters should increase and another voltmeter should decrease, right? So, like, you know, it's a little bit of a mess, but I'm just trying my best here. So I'll connect this here and oops. Okay, so we're going to start from this is at 0. So if this is at 0, what happens is one of them will get the entire PD across this, which is this voltmeter at 9 volts. And the other one has no voltage across this, which is this. Now watch this. This is going to be cool. So mystery student, watch this too. So basically, we're going to be sliding this. Are you seeing that? That's at 0 and the other one's at 10. So as we move it, you're going to see this voltmeter increasing because the resistance between these two ends are increasing. And this is going to decrease because the resistance between these two ends are decreasing. Right? Are you seeing that? If you notice at any value, for example here, what's the value here? 4-ish? It's 4. Okay. Guys, you can see that, right? It's 4. It's moving around a lot. Yes, this one's a very emotional voltmeter, sorry. It's dead. Okay, I think I broke this. I broke it. Come back, please. Oh man. Okay, it works now. Okay, I will need your help. Hey, Tazib! We need someone to move the rheostat. Okay.
1 minute lag.
Okay. Okay. So as you can see, that's 4 volts on this voltmeter, and this is 5 volts, right? Okay. Oh, come back. No, not you. The voltmeter. Yes, it's back. Oh. Okay. Now, yes. If you move that, you're going to see these values are going to change. Aste aste move karo. Oidike. Yeah. Keep move.
Touch screen?
Yes. No, it's not touch. Okay, so you'll see this is constantly increasing. It's gone above 5 now, and that's gone down to 4. And if you go even further, this is going to go all the way up to 9. Keep going. And that's at 7.5, and that's almost at 0. Basically, this is calibration error in our voltmeters. So that's basically what happens. Could you do us the honor of going back to the other end again, please? Thank you. Thank you very much, Nafiz. So again, we're starting. This is at a high voltage. That's because the resistance across it is high, and this is at a low voltage. So as we move this, good job, great job. Yes, now they're both moving in the opposite directions, and this is decreasing, and that one is increasing at any value. If you see the values, for example, now it's around 3 and 6. Actually, it's very temperamental. Oh, it's gone to 0 and 9. So it will always add up to 9 volts. There you go. Yay. Okay, get rid of this. Oh.
Clap reacts, guys.
Yes. No, laugh reacts, not laugh reacts. What the hell, man?
Clap
or clap reacts. Is there a clap react?
That's it.
No problem. All right, guys.
এটা আবার practically করে দেখান লাগে আজকাল মানুষ।
না এটা প্র্যাকটিক্যালি দেখানো তো ভালোই, like you know, এটাই তো
All time
দেখানো
we just said it and we imagined it.
but like wouldn't it be better if I actually showed it to
We
you
had
guys?
enough capabilities to imagine that.
Okay, guys, let us continue with education. So let's draw what we just did. We have the 9-volt power supply across a variable resistor, right? And we put one voltmeter here, and we put another voltmeter here. That's basically what we did. So what basically happens is as you shift this, one of them must increase, another one must decrease. And this is exactly what the potential divider circuit is, because both of these has to add up to the EMF of the circuit. So if the EMF is 9 volts, so we saw a scenario where one of this was 4 volts, the other one was 5 volts. If we were to move this direction, in this direction, then this value will decrease and this value would increase. But their total sum, basically V1 plus V2, will always be equal to the EMF here. It's going to be 9 volts. So that's basically what happens here. So basically 4 volts and 5 volts. And that's basically what goes on. All right. So we have this whole thing going on. And an important thing that you have to understand here is that the EMF is always going to be equal to the PD. So we can actually work on this and take this further into explaining the potential divider circuit. Let's draw this a little differently, all right? I'm going to draw this with a little bit of a variation. All right, now what I'm doing is instead of drawing one resistor, I'm drawing two resistors, and it's pretty much the same. I'm basically splitting this into two parts, right? Basically, this is going to be one part, and this is going to be another part. If we do this, again, we have one voltmeter here and another voltmeter here. And if this resistance increases, the voltage across this increases. But an important thing is, if this increases, this must decrease, because the total EMF must be always equal to the total PD. So there's an easy way of turning this into an equation. So say this is a variable resistor. We call this R1 and we call this R2. So the easy way is, because V is equal to IR and the current is the same through both resistors, then we can say the voltage is proportional to the resistance of each resistor. So given that this is the scenario, if I increase the resistance of R1, that's why the voltage of V1 is increasing. And as a result, if this increases, this must decrease, because the EMF must always add up to the same PD. So we can build this into an equation. For example, V1, if we want the value of V1, all we need to do is, we don't even need to do the calculation for the current or anything. All we need to do is actually, we find how much R1 is of the total resistance. So R1 divided by R1 plus R2 into the EMF of the cell. That gives us basically the V1 value. And similarly, if we want V2, then what do we do? There's two ways of doing this. One is obviously the method that I was mentioning, is you subtract V1 from the EMF, and you're going to get V2. But if you want to calculate it directly from here, it would be R2 divided by the total resistance, which is R1 plus R2 into the EMF. Right? So these are the two different ways in which you can find the V of each one. And from this, we actually do come up with a potential divider equation. So what would the potential divider equation be if we simplify it? So let's draw a slightly different circuit where we have two resistors, right? And say that we call this V out. So what will V out basically add up to? Ooh, so many wires. So what will V out add up to? So if this is resistance 1 and this is resistance 2, so, and it doesn't really matter, you can keep them variable or constant or whatever, and this is our EMF E, then basically V out is going to be the ratio of the resistances of how much this is of the total resistance into the EMF. So V out is going to be R2 divided by R1 plus R2 into EMF. Right? And that is basically the easy way of doing it. V out is equal to R2 divided by R1 plus R2 into EMF. That's it. So further variations of this circuit, instead of having resistors, you can have other things. Can you tell me what other things we could have which varies with resistance? Any ideas? Anyone? Anyone? Yes, you know this one?
Light sensor.
Yes, photosun. That is basically
LDR.
LDR, that's right. Oops. LDR. Light dependent resistor. Do you know what happens with the light dependent resistor with brightness? Resistance versus brightness?
Inverse common.
Basically, as the brightness increases, the resistance decreases. Excellent. And there's another device which is sensitive to change in temperature, which is a thermistor. And it also has a similar sort of graph. We can just simply show it like this also. Sorry, resistance versus temperature. As the temperature increases, resistance decreases. It's also called NTC, negative temperature coefficient. Why? Because as the temperature increases, resistance decreases. Basically, the gradient is negative. So based on these sort of circuits, we can create one last variation, which is going to be, let's draw this. Let's use a different color. It's getting boring with the same color. Got green. So, say for example, I draw a circle like this. I have this, and this is basically, can you tell me what this is, mystery student?
LDR.
Yeah, that's right. And do you know what this is?
Thermistor, no.
Yes, good job.
Okay, good.
So say this is V1, and it across we get V2. So can you tell me under what conditions will V1 be high?
Do I answer that?
Anyone can actually. Everyone's like thermistor, 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 thermistor.
Yeah, ওইটা resistance কমবে ওটার বাড়বে।
So basically this is going to have a high resistance across this. It's going to have a low resistance. When does an LDR have high resistance?
When the temperature is
LDR,
sorry, light is
when it is
intensity is low.
low. So basically dark, right? And এটার সাথে কি থাকতে হবে?
Temperature low.
Yeah, so the resistance across this has to be low. So this,
The-
because
the
it's a
temperature
thermistor,
high হবে।
so dark and hot. So under dark and hot conditions, the value of V1 will be high, right? Under what condition? And obviously when V1 is high, V2 is going to be low. I know? This is high, this is low. When does this happen? Under this scenario. And the other scenario is, say V2 is low, and sorry, V1 is low, and V2 is high. Under what conditions will this happen?
Low
When the resistance across this is low, which is going to be bright,
that's going to be cold. No.
and that's going to be cold. Correct.
Cold.
Cold will later across a resistance high over thermistor now. So that's going to be high, and basically that makes it cold. So yes, that's it basically. So this is basically the approach to potential divider circuits, and that's how we come up with this sort of stuff. So that's pretty much it, guys. We're done with this. We tried to show a couple of practical situations and experiments of how to actually do this, and these would be the basics of the potential divider.